and welcome to the 10th session of the Porous Media Tea Time Talks. With these seminars, we want to give junior researchers working on porous media the chance to present their work to the scientific community around the world. These sessions are meant to be complementary to the geoscience and geoenergy webinars, which you can find in our featured channel. My name is Catherine Spuren, I'm from Imperial College, and I'm joined here with my co-organisers, Kamal Singh from Heriot-Watt, Mohammed Nouri from Oslo University, Tom Boltries from Ghent University, and Maya Rucker from TU Eindhoven. And we also have Marcel Mora from Oslo University, who is joining us in spirit today. And I will now hand over to Mohammed, who will introduce our first speaker of these talks.
Thank you very much, Catherine. Today's first presentation is by Ankita Singh. Ankita has recently submitted her PhD thesis titled Computer Vision and Texture Analysis of X-ray Images of Rocks. Her PhD focused on extending the current digital rock physics workflow by texture analysis techniques for direct use of raw microcity images for rock characterization and REV analysis. Today, she gives a talk about raw microcity images and machine intelligence for inferring REVs. Thank you, Ankita, for joining us, and the floor is yours.
Ankita, you're on mute, sorry.
Thank you. So thank you for the introduction, and hello everyone from the land of kangaroos and koalas. Firstly, I would like to thank everyone from the Porous Media team for organizing these talks and giving me this opportunity. And I would also like to thank Payman Mostagimi for nominating me for this talk. So before we understand why machines are intelligent enough to estimate REVs from raw microcity images, let's look at a scenario. So imagine you're blindfolded on a sinking boat, and you know that there are two ropes on your boat. One is a polypropylene rope, which is actually used to make lanes in a swimming pool, and the other is a manila rope that's used in a tug of war. The only problem here is, since you're blindfolded, you do not know which rope is which. So how would you quickly identify what kind of rope do you want to use to save yourself? The quick answer to this is, you identify the rope by feeling it. Because when you feel rope 1, which is actually the polypropylene rope, what you would feel is it as lightweight and something soft as velvet. But when you feel the manila rope, it would feel rough and scratchy. And by feeling the rope, what you're actually trying to do is you're trying to analyze the texture of the rope. So the question then is, do rocks that we study exhibit texture as well? So let's look at a range of high-resolution microcity images of rocks. So what you're seeing here is a sandpack. You're seeing some sandstones, and then you have some carbonates. Now, here are how 2D slices of these rock look like. And from their first inspection, what you would see is that you have different features in a rock. There are some light minerals here. There are some dark black regions, there are some gray regions, and you see that they are spatially arranged differently, which is what is texture. So texture looks to characterize how bumpy, how rough, how the grains are arranged next to each other. What we traditionally do to analyze these features in a rock is we visualize it using a histogram. And what this histogram tells us is, it tells us the frequency of gray level intensities, which is what you see, these pixel values here, and how frequently do they occur. So for example, for a sandpack, you would see two peaks, one representing the pores. Pores are empty spaces that hold oil, gas, or air. And then you have these grains, which are quads. Similarly, for a Bentheimer sandstone, you would again see two peaks of pores and quads. This is a fieldstone example, and what you're seeing here is that you have pores, which are the black region, quads, which are the gray region here, and the light gray are the glauconites. For the Wilcox sandstone, the histogram looks pretty much like a single peak having quads. It actually does have some pores around, and it does have minerals, but it's not quite evident from this. When we look at the Austerlitz carbonate, you look at the macropores here, which are these black spots. You have microporosity, sub-resolution porosity that you cannot really see clearly from the resolution sometimes that the rocks are imaged at. So these are these gray regions here, the darker gray, and these light gray regions are mainly calcite. The same thing with the ketone carbonate, you see calcite as the main peak. So these are all your calcites. And sometimes you again have microporosity either inside the grain or in the surrounding here. Now, the main phase that we are interested in is pores. We want to see how connected these are, how pixels of pores are spatially arranged. But we don't really have a method that we have been able to develop that can directly look at grayscale and analyze the textures of rock or understand the spatial arrangement. So what we are going to look here is a method from the medical imaging called as gray level size zone matrix. This was initially designed to classify cell nuclei and look at its texture. The way this works is that you have a grayscale image, and then you have numbers representing each of these grayscales. And you then, using this grayscale image, develop a gray level size zone matrix. So the rows here represent your gray levels, so 1, 2, 3, 4, and then you have something called as a size zone. Size zone looks at how connected your gray level intensities are. So for example, if I say the gray level intensity 4 occurs as a connectivity of 5 one time, what I mean to say is these gray level 4, 4, 4, 4, 4, they are 5 fours together and they occur once. So that's how you populate this matrix. So basically, you convert a 2D or a 3D grayscale image into these beautiful two-dimensional matrix that can now look at connectivity of individual grayscales and how frequently they are connected. So when we look at the GLSZM of the microcity rocks, what you now have is that you have an additional information. The histogram only told you how frequently a gray level occurred, but a GLSZM can tell you the gray level intensity, how is it connected, and how frequently it occurs. And this is a log scale representation. The colors on your color bar and your z-axis represent the same thing. So what you would say, how you would interpret this is as a gray level intensity of 50 occurs as a connectivity of 250 about, say, 10 times. So that's how you would read it. So just like you saw in the histogram of pores and quartz, you'll see, again, two peaks of high connectivity, which are the pores and the quartz. And you again see the same thing for Bentheimer sandstone. So this is the highly connected region because the connectivity increases. You have that for pores and quartz. For fieldstone, you see we had two peaks here, which are again represented quite clearly. The glauconite was not really clearly distinctly visible, but then with the GLSZM, because you're not looking at connectivity of individual phases, you can see this quite clearly over here. The same thing occurs with the Wilcox sandstone. You didn't see the pore peak is not very clear, nor are there many of these high density minerals here. But with the GLSZM representation, you can clearly see that there's a peak here and there's another peak here representing pores and the high density minerals. The same thing occurs when you look at carbonates. One of the key features of a carbonate is the presence of microporosity. And so when you look at an histogram, it's quite difficult to figure out where the microporous region lies because there isn't quite clear the bifurcation. And this is how the GLSZM looks like, where you have the connectivity and the two peaks clearly seen. The microporous region, if I zoom in, so if I zoom into this area, this is how the microporous region appears. So you still can see a distinct peak here of the microporous region, which is quite an advantage when using the GLSZM method. And even for the ketone carbonate, you see there is an extended region which indicates the presence of microporosity, but the GLSZM has this distinct signature peak of the micropores, which again tells you that, yes, there is a distinct peak of microporosity. So what do we do after this is that once we've calculated the GLSZM, we can then calculate statistics, which can be treated as proxies for porosity and permeability. So the way we do it is by calculating something called as a low gray level emphasis, where we just emphasize these low gray levels. And you have smaller connected regions and you'll have large connected regions which characterize your entire pore space. And we do that by adding weights that is have a denominator of gray level intensity square, and that gives you your entire porosity, and we treat it as a proxy to it. Then we look at large area low gray level. So this only emphasizes the highly connected regions that represent your pore space. And we do that by not only weighing it with respect to the gray level intensity, but also adding another factor of connectivity. So you have connectivity squared divided by the gray level intensities. So it emphasizes this region. So we've discussed about the textures, we've discussed about the statistics, but where does this all fit in? Traditionally, what we do is that we get raw microcity images, we segment the different phases out. So this was your sand pack, and we get the grains and the pores, and then we carry out flow simulations. But what now we can do instead is that in this step, when we lose a lot of the textural information, we lose mineralogical heterogeneity, we lose the connectivity of pores and minerals in terms of the gray levels, and also sometimes the microporous region. And you've kind of lost the texture when you're moving from the grayscale to the segmented phase. And one of the papers really mentioned that if we want to address using the raw microcity images and we don't want to lose information, we need to incorporate the texture of the rocks. And the next thing is, when we carry out flow simulations, it's computationally expensive and time consuming. If you want to do one calculation, it might seem reasonable, but then if you have to do multiple calculations, which we will see in the next slides, it's quite computationally intensive, and there's a lot of work. So what we can do instead is that instead of segmenting, we could complement the whole process by carrying out the GLSRM technique and then calculating proxies to porosity and permeability. And one such application is elementary volumes. So when we go from different scales, we need to make sure that at every scale, we capture the representativeness of the heterogeneity. By that, I mean, if we are looking at the pore scale, we are measuring permeability, we need to go past the fluctuations to the point where there's a plateau. And so REV can be defined as a volume that's large enough and has captured heterogeneities of a particular property. And so when we go from a smaller region all the way to the big region, you see the fluctuations, and what you are aiming to reach is the plateau. So what I'm going to show you now is that given we have the GLSRMs and we have the statistics, which can be treated as proxies to porosity and permeability, how do they compare to those that we calculate from the segmented images directly? Do they follow the trends? So here's the first REV analysis. And what I would like you to concentrate on is these two curves. The red curve shows us the porosity calculated from the segmented image, and the blue curve shows us the low gray level, which is treated as a proxy to the porosity calculated from segmented image. And you can very clearly see that it does follow the trend even when calculated from the grayscale image. And so the REV is at a point where it tapers, so this would be around 120 voxels. And that's for the porosity. We verified it with the literature, and the same thing happens with the permeability. You see the trends are followed very clearly. And then we identify the permeability here, the REV for permeability and the grayscale image as 200 voxel cube. The same thing with fieldstone, we repeat the same process, and what we again see here is the trends are followed. For the fieldstone, with the image size that we had, we saw that the porosity REV was reached quite close to the maximum image size, around 460 to 480 voxels, which is over here. For the case of permeability, we found that there was no REV because you could still see the increasing trend in both permeability and the large area gray level emphasis calculated from the GLSRM. And this is again verified from the literature, when we looked at the ketone carbonate, and we again saw that the trends were followed in case of permeability and low gray level emphasis, and the REV lied at around 200 voxel cubed. The same case happened for the permeability when we see that the trends with both grayscale and the segmented image permeabilities matched around 400 cubes. So the other thing I would like to mention is the time. So the amount of time that took for us to look at the GLSZM based calculations, which were carried on the same computer as the permeability calculations, the entire analysis that I showed you for the deterministic REV, that is the REV that grows from the center, that was finished in about 4.6 minutes, which compared to about 242 minutes when we do the porosity permeability analysis. And so we see that using the grayscale images and the texture analysis, we are about almost 53 times faster. So when we ask the question, are machines intelligent enough to estimate REVs from raw microcity images, we address this by considering that raw microcity images are important because they have the texture of the rock, where we incorporate information like mineralogical heterogeneity, connectivity of pores, microporosity region. And if we don't consider it, we lose the spatial information. So in order to incorporate this, we use texture analysis of porous media using a medical imaging technique, which incorporates how these gray levels are connected. We were able to find two statistics which could be used as proxies of permeability and porosity. And lastly, we applied our knowledge of grayscale images to infer REVs, and we saw that the trends for the grayscale proxies and the segmented image porosity and permeabilities matched quite well, and the REVs agreed. So this is what I want to talk from today. And so we can say that using texture analysis technique, we have been able to provide a robust analysis to estimate REVs. And therefore, we can say that, yes, our machines are intelligent enough. You can find more information on the paper here. I also have the code and the data available. So please feel free to contact me if you have questions. But apart from that, yeah, that's all about the talk. So I'd just like to thank the team again for having me, my supervisors, collaborators, and Tom Baltres for giving me the images for this study. Happy for you to contact me, and here are some links to the related work. Thank you.
Thank you, Ankita, for this beautiful presentation. I really enjoyed it. So it's a very new information.
Yeah.
So bringing from the raw images. For the audience, if you have any question, please type in on the right-hand side of the window. Just like I would like to ask or comment. So it also for the carbonates, it would depend on image resolution, right? So you have you tried different image resolution available in the literature?
So sorry, let me just show you. So when I was looking at so ketone carbonate in this case was a good example because the sub-resolution porosity is actually decently resolved in this image, but then when you apply to some other images where the intensity difference between the microporosity and the grains are very minor, you cannot pick them up in the GLSZM because again, this is just an intensity based method. So this could act as a complement to cases where you're using a dye to highlight the microporous regions. But then this definitely helps us segment in case you do not want to go through that method and you want to still identify where the intensities could be. I think this is worth definitely giving it a shot. Yeah.
Cool, thank you. And anybody in the studio have any question? Please do ask. And what's your, may I ask, like what's your next plan? So what are you going to do with the further with the data or with the analysis, or maybe it's a secret? You don't
Not really. Not really. Yeah. So I think these techniques are quite new, and one thing I would personally would like to do is actually Wilknot, when she had come and looked at my poster in one of the she mentioned how noise and resolution, like even you mentioned, can affect these statistics. So I think the next step would be consolidating everything that I've learned from this study and doing a little bit more sensitivity analysis, and also adding physics to it, because this is a very image-based approach. And if we can incorporate physics and really relate the grayscale statistics to the segmented porosity, permeability, I think that would be a really big step for the digital rock community. Yeah.
Yes. And we have a question from Martin Blunt.
Oh.
So, could this be applied at a full core scale with good quality images used to identify rock types in a heterogeneous medium and the REV for both modeling and for subsampling of the core?
Okay, so the first part of the image where you're saying can it be identified, can it be applied to full core scale? Yes, so as long as you have distinctive features, this method is applicable, is universally applicable. In fact, this technique actually has been already applied to medical imaging in terms of brain scans, in seismic connectivity of fractures. So definitely, I think, identifying heterogeneous medium would be a very good candidate. Um, because you've asked that question, I would also like to mention, so my first paper, I have provided the link in the end of the presentation, that looks at more characterizing the rock from the perspective of comparing grain sizes, looking at noise in the image. So I think that would be a better candidate in terms of analyzing the heterogeneous medium. And this is more about connectivity of pore space. So it really depends what sort of application you're looking at. And the RAV for both modeling and subsampling the core, yeah, definitely. Yeah, this, as long as you have, like you mentioned, good quality images, this method can definitely be applied. And I'll be happy to try if there is something that, yeah, some images are available for that. Yeah.
Cool.
Thank you.
Fantastic. There's another
Yeah.
question from Ali Riani. He asks, what is your impression of imaging artifacts at the micro scale, like blurring and image noise, and how it may affect your analysis?
Yep. So I have, but I have personally refrained from using images that have ring artifacts because it's quite difficult to quantify the effect of ring artifact. But if you're looking at just general noise, you see what the way this method works is that because you can look at each individual gray level and how it's connected. If there's a lot of noise, what you would see is that there'll be a lot of these single gray levels distributed across the image without having much connectivity. And so these would occur as these really high values of low connectivity. And so you could characterize it based on that. If you're asking what did I do in this setting, I actually have not used any image filters. This is just raw image right from the scan. The only operation that I've done is reducing it from a 16-bit image to an 8-bit image, which in a sense also does reduce some amount of noise because, in a scan, you do not use all the way from 0 to 65,000 bit values. You use only a small range of it more often. So yeah, reducing it has to an 8-bit has sort of dealt with noise to a certain extent. But these methods, if there's a lot of noise, it would show up quite distinctly in these cases, and you would not have a lot of connectivity because the noise literally destroys the connectivity of any gray level. Yeah.
Thank you, Ankita.
Yeah.
We have a question from Said Sadegh Junaid. Sorry for mispronouncing the name. So he asks, the method is based on connectivity of voxels. So can it be implemented for tight rocks like sandstones and carbonates?
Yeah, so it depends on what you're trying to gauge from applying it from the tight rocks. It will still give you, so for example, one of the tight rocks that I applied it to was, sorry, give me a second. Let me just go. Yeah, so this is the Wilcox sandstone that you can see here. This is a tight sandstone that I got from Digital Rocks portal. And, if you're looking at being able to identify pores, which is quite difficult from this, you can see that the GLSRM still picks up a pore peak over here. It does not pick up the microporosity because the resolution and the image, I think, needs a better quality in this case. But if you want to apply this technique, yes, you can definitely apply, and you can characterize the macroporosity peak. And if you have different minerals, if you want to apply it and actually have the microporosity also captured, I think for that you would need a good resolution image. For example, the ones over here, they were quite good in resolution, so you would be able to capture the peaks clearly. But then again, yeah, I haven't really investigated it as this is the one image that I've tried. So yeah, again, if you have more images, please feel free to contact me. And the code's available on GitHub anyway. So yeah.
Oh, that's cool.
Yeah.
There's a question from Mohammed Nuraipur. So can we use this technique to map mineral dissolution of precipitation using the raw images?
Yeah, as long as there is a difference in the intensities, and we could use some clustering techniques on these maps that will allow you to then, identify regions that are different from your original grains or quads, if that helps. Yeah.
Cool, cool. Thank you very much. And there are some messages for you. Thank you from Martin
Okay.
Blunt.
Oh,
And
thank you.
also, thank you from Ali. So he said you've already answered the question before I asked you.
Okay, thank you so much for your feedback. Yeah.
Okay, with this, we'll finish the talk. Thank you so much,
Yeah,
Ankita, for this
thank you.
wonderful presentation. And we wish
Thank
you
you.
good luck for your future.
Thank you.
So now let's move on to our next talk. So it's my pleasure to introduce you to Mousa Hosseinimehr. He's from
Right.
Technical University of Delft, and he's working on modeling of fractured reservoirs. So Mousa, the floor is yours, and we're looking
Okay.
forward to your talk. Thank you for joining us today.
Yes. Hello, everyone, and thank you for hosting me. And today I'll talk about the scalable simulation models for fractured reservoirs with complex geometries. And I work with Cornelis Fout and Hadi Hajibegi, and I'm part of the Delft Advanced Reservoir Simulation Group, or DARSIM. So, like many other fields, in our field, it's important to have accurate and proper computer models and simulations in order to have a better understanding of physics and chemistry down there, and also for decreasing the financial cost. Now, in porous media field, there are many applications for our simulations. It's hydrocarbon exploitation, geothermal industry, carbon capture and storage, and energy storage. And today I want to talk about mainly of the fractured modeling, but also I want to show you an example of the governing equation that I use in my model, in this example for multi-phase geothermal fluid. So I have two sets of equation. One of them is the mass balance equation. You have the mass accumulation, and then you have net flux mass in minus out. So then net flux, net mass flux, and then you have the mass source term, and you have the pressure as the main unknown in this equation. The other one is the energy balance equation, which you have the heat accumulation, you also have heat convection flux, heat conduction, and heat source term. So there are some terms that maybe you are not familiar with, so I'm just pointing them out. This is U as the internal energy, D is the conductivity coefficient, and T is the temperature of our system, and H is the other main unknown that we are using in this system of equations. So the simulation approach that we have is fully implicit. We couple the two equations together, we write the equations in the residual form, so mainly right-hand side minus left-hand side, and using Newton-Raphson method, we linearize the system, and at the end, we have this package of the linearized system of equations that we have. This is Jacobian, the derivative of our residuals of each equation with respect to the main unknowns. You have the vector of the update of the unknowns, and then you have your residual. So in mathematical notation, when I write it in a short way, this is the system that I am solving. Now, the problem is we have a huge computational challenge in front of us. We have fractures in almost all the reservoirs and the porous medias. Now, the thing is, I'm just going to give you a couple of examples here. You see that the networks of these interconnected fractures can look very complicated, and they have complex geometry, and they may have heterogeneous properties. And these fractures have heavy impact on fluid and heat transport in our system. And I'm just going to show you an example that I have a fracture, horizontal fracture in the middle, and the moment that flow starts reaching the beginning of the fracture, it gets transported immediately to the end side of the reservoir. So these fractures have very important influence on the fluid flow patterns that we have in our system. So it's very important that we model them accurately, we capture them accurately in our simulations. So obviously, I cannot discretize my system down to the aperture of the fractures, which is in millimeters, while having a reservoir of the scale and extent of kilometers. This will end up in billions of grid cells, and this is not efficient and practical for using that model for simulation. So we need to use a smarter way. So there are many fracture models out there that capture the fractures explicitly. One of the models that I'm focusing on is projection-based embedded discrete fracture model, and I'm going to say short PDFM. So in this model, you have independent discretization of rock separate from the fractures, and this creates a simpler gridding structure, and it avoids that excessive grid resolution that I told you about. And giving all the geological uncertainties that we have down there, it is accurate enough to capture fractures with different conductivity. Some fractures can be highly conductive. Some fractures, I call them fracture, you call them flow barrier or faults, could be sealing, so they may block the flow. So in this example, you see how a fractured test case is discretized in a separate way. So the rock, or we call it the rock matrix, is discretized in a completely independent way, as if there were no fractures, and the fractures are discretized again independently. Then they are put together, they overlap each other, and then you detect the connectivities and the overlaps in your model. And this has been done in 2D, and also has been extended to fully 3D geometry for fractures in the system. You can see the references here. If you're interested, you can have a look. And there is a difference between embedded discrete fracture model and projection-based embedded discrete fracture model, EDFM versus PDFM. In PDFM, one of the shortcomings of EDFM was resolved, which was EDFM was not able to capture the fractures where actually were flow barriers, so they were blocking the flow. Due to this parallel connectivity, which I'm going to show an example in the next slide, so you'll see the difference. This was resolved by obtaining the projection of the fracture plate and the fracture cells against the interfaces of the grid cells in the matrix rock and the rock matrix, and this was resolved. Now I'm going to show you an example of how the difference of these two are showable. So I'm just going to show you a simple example. There are a network of just a cross fracture in a box, in a 2D box, and I am injecting from the left, and I'm producing from the right. Now what I'm doing is that I'm discretizing this in two approaches. One of them is DNS, a direct numerical simulation, where I'm not having any explicit fracture model, and I have to obviously discretize my system down to the aperture of the fracture, which is 375 by 375. On the other approach, I'm discretizing the system into 75 by 75 grids, but having the fracture model, EDFM or PDFM model. This makes it easier for discretization. You don't have to have excessive resolution. Now, if you have fracture, which is 10 to the power of 8 times, basically, more permeable than the permeability of the matrix, then this is what you would get as a direct numerical simulation. So this is an exact simulation or a result without having any fracture model in your system. Now you see that PDFM and EDFM can capture, both of them, this different pressure drop that you have due to the existence of this horizontal fracture. And you can also see how the cold front, this is a geothermal simulation, how the cold front is reaching and going through to the other side. So both models can more or less accurately capture what is actually happening in this system. Now, if we have fractures that are actually flow barriers, so they are 10 to the power of 8 times less conductive than the matrix. Now, this is a different scenario. You will see at the location of the vertical fracture, which is against the direction of the flow, a huge pressure drop. Now, DNS shows it, PDFM captures it, EDFM, due to the existence of parallel connectivity, fails to show it. And now you can see also as the cold front is passing through, with the EDFM model, we cannot capture this pressure drop and this blocking of the flow. So it's important that we use PDFM instead of EDFM, especially if we have fractures with different conductivity ranges. Now, on top of that, the other issue that we have is the shape of the reservoir. we cannot model what is actually happening down there with just Cartesian boxes. We need to be able to discretize the system, including the geometrical complexities of our geological model. Many fields of industry related to the simulation model use corner point grid structures. The corner point grid structures, or the geometry, as the name says it itself, is that the shape of the discretization around the cell is based on the corners. So there are 8 corners, 4 top, 4 bottom, and that creates a hexahedron. And the connectivity between the hexahedron are calculated based on the 2-point flux approximation. And we use that in our also DARSIM simulator. And we use, by the way, MRSC functions to read the eclipse models, or the models that were related to the geological relevant grid geometry. Now, what I did is I tried to develop the PEDFM fracture model for corner point grid geometry, so that we can have fractures explicitly captured and represented in those models. Now, obviously, it's the same concept, but the implementation is a bit more complex. So again, you have the fracture plate. You have to obtain the projections of the fracture plate against the interfaces between the matrix, rock matrix grid cells, and then obviously the angle where the inclination of the fracture plate is based on, has an important influence on the calculation of all these projection connectivities. Now, this is calculated based on this formula. And you can see an example that there are 2 fracture plates in one of the shape of the hexahedrons that we have, and they can form different polygons, and all those polygons have to be captured accurately in order to find the connectivity, the accurate connectivity between every fracture element and all the matrix cells that are overlapped by that fracture element. This way, we can avoid excessive resolutions in terms of having faults and fractures in your system, even in a geologically relevant field, which is a very important approach in my view. Now I want to show you some examples, what we did in our simulation model. This is a Delft reservoir model, which is from where my university is. And in this formation, which is actually a geothermal formation, you have a scale of 10 by 2 by 10 by 2 kilometers by 100 meters. So it's a huge domain. And the skeleton is about 1.3 million active grid cells, the cells basically that you can see in this domain. And you have, of course, heterogeneity. You have permeability of the reservoir from 10 to minus more or less 15, I would say, up to 10 to minus 12. So you have about a bit more than 1,000 contrasts in the permeability in this domain. Now, I just wanted to see if my model can handle such a test case or not. I just ran a simulation, and this is, I'm injecting from here, producing from there. These are vertical wells, and this is what you see as a pressure field, high pressure all the way to lower pressure from injection to production. And this is what you see as the flow is happening from the injection and going all the way, and due to the pressure drop goes towards the production well. Now, the thing is, this is the important reason that I wanted to mention this test case. This test case has a lot of grid cells, and you may not see it in this picture probably, but there are so many discontinuities in our system because of due to the impermeable layers, due to the fractures and faults. Now, if we can use PEDFM model and capture all those fractures and models and all those fractures and faults accurately and explicitly in our model, we can avoid excessive resolution and so many million grid cells, and we can have a better and more efficient simulation for such system. Anyhow, this is another simulation that I have, which is a Norne field, which is in the North Sea, and I modified it myself just to put some fractures and faults in it, and I just wanted to see how it runs. And what you see, there are about 45,000 active grid cells. We have a heterogeneous field, and I just added 15 fractures myself. And I am injecting from these 2 points, 2 vertical wells, and I'm producing from the end. This is all just only my imagination. This is not a realistic what's happening actually in the North Sea right now. And I just wanted to see if I can use the PEDFM to capture the fractures and faults explicitly and model it for such a field, which I eventually could do that. Now, the thing is, apart from the challenges that I mentioned, we have more challenges. The another challenge, as I mentioned, is the huge size of the domain, and we need a scalable simulator for it. The resolution, do we need excessive fine scale resolution everywhere in our system? I would say no. We need the resolution wherever the physics happen, wherever the front is passing by. So we need to have an adaptive resolution. And we have a strong coupling between heat and mass transfer in geothermal systems. So we need fully implicit method to capture them. And we have heterogeneity and fracture. So we need to have fully coupled operators, and we need to have PDFM to capture all those fractures. In short, we need a smart and advanced simulator who can handle all these challenges, can address all these challenges together. And I want to talk about algebraic dynamic multi-level, which is something that I, together with Matteo Cusini, have been working on, and we developed a few years. There are some references. If you are interested, you can have a look at. And this algebraic dynamic multi-level, or ADM method, is dynamic. So it can capture the front, as you can see, as it goes in finer scale, and it can keep the rest of the domain in a coarser scale. So that improves the efficiency of the system. It uses multi-level, multi-scale basis functions. So this way we can capture the heterogeneity. If you are interested, you can also check out papers, and these things are mentioned in details, and that now is not the time to explain it in more details now. It is also algebraic, so everything are multiplication by these matrix and operators that creates a better computational efficiency if you're running highly and large scale models. Now I want to show you just one result. This is a 2D domain. I have 30 fractures, some highly conductive, some lowly conductive, and you have a heterogeneous domain. And I am checking to see how ADM works. So we have fine scale, and what you see, this is captured in fine scale without any ADM. And now I want to show you how ADM with different tolerances can capture more or less the same front without using that many fine scale resolution grid cells. So as you see, by even decreasing the tolerance, which again, you can check our papers and see what these tolerances actually mean, you can see how the number of active grid cells at fine scale are reducing, but still I am able to capture the shape of the front at that specific time step in my simulation, which is a very important aspect of simulation if you want to do. Okay, to summarize it, so what we saw is that PDFM was accurate and efficient enough for discrete fracture modeling, and it created great flexibility for us. And I was able to apply it also to complex reservoir geometries with corner point grid and relatively geologically relevant test cases. And actually, we have developed this PDFM package for coupled flow and heat in heterogeneous media in our DARSIM simulator. And this is the link. It is available publicly in GitLab. So feel free to go and explore it and see, and give us just feedback if you're interested. And also the algebraic dynamic multi-level is quite scalable for field scale simulations. And the next step for me would be to couple these two together for complex reservoir geometry. So having corner point grid, ADM, and PDFM all in one package, so we can have something to present to improve the efficiency of the simulations while keeping the accuracy at a desired level. Thank you everyone for your attention. If you have any question, I'll be happy to answer if I can. And if you're interested, just contact us and let us know what you think, and any collaboration, we are open to it. Thank you.
Thank you, Mousa, for this excellent presentation. In the meantime that you are typing in your comments and questions, I have a question to you. For example, when we want to model fluid flow for the CO2 storage, and we are dealing with a fractured zone or fault zone, we have a core to handle, and also we have a damage zone. Do you have any suggestion how to handle connectivity and pressure communication in the core and in the damage zone, and how to capture the enough resolution in order to be sure that we don't have any leakage?
That's very actually important thing that you mentioned. So the thing is, we need to be able to capture the resolution at the location that is important for us. This is not just by the change of the front of the flow and heat that is happening. It's also important to have the grid resolution accurate in a high resolution, even in the locations that we think that is important for us, because there is a fault, or there is a damage, or there is anything that we have added ourselves to increase the contrast of heterogeneity in our system. So I think it's very important to keep in that region also a high resolution grid in order to be able to capture it in a desired accurate level. Yeah.
I have a quick question. First of all, thank you very much for this great talk. I really liked it, and also it was nice to see that you can capture permeability contrast, especially when you have quite high permeability in the matrix, and then you can really use a PDFM model to capture those details, especially for the flow. I have a naive, maybe more general question, and it's more naive. How do you generally validate these models?
So basically, depends. What part of the model are you talking about? If you're talking about the ADM or the algebraic dynamic with different resolutions of coarse scale and fine scale, we basically can benchmark it and compare it with a fully fine scale resolution. So that would be basically the exact, we call it exact solution, the result. Now with the corner point grid geometry compared to a different model, there is no reference to it, basically. So you have to just compare the result together, but you cannot calculate something, as you call it, as error. Yeah. But the benchmarking would be basically the performance comparison. Yeah.
Okay, cool. Thank you.
We have one question from Leila Hashemi. Thank you for this great talk. Would PDFM concept work for the complex?
That's a very excellent question, I would say. And I'm going to say yes, absolutely, because the fluid models are kind of a modularly different concept than the discretization in your simulation or your model. So whenever you have this fracture modeling captured via your fracture model, you can use it for different complex systems. Now the thing is, with capillarity, this is a tricky subject, unfortunately. So if you have capillarity and you have fractures, very thin layers, plates of fractures connected together, capillarity could be defined in a very different way than how it is defined in other systems. If you want to capture the capillarity in between the fractures, while we have PDFM or we have captured the fractures explicitly, maybe it's good to look also into how capillarity behaves in our lab in the pore scale, so we can be sure that we are including models accurately in our system. But in general, I would say yes, definitely.
Yeah. And the second part of the question, also connecting it to the previous speaker, can pore scale modeling be directly connected to ADM framework? Say, for example, by using consistent function from pore scale.
I would answer yes, definitely. And this is actually the strong point of scalable simulations, because we know that people are working on lab, and in the pore scale modeling, we can see that the behavior of the fluid flow and the pattern that we see in the pore scale is quite different, which is in a scale of millimeters and centimeters. And now we are talking about models of order of kilometers. The good thing is that if we can somehow apply ADM for pore scale and larger scale together, we can have different dynamic grid resolutions. We can make it, we can have an approximation of what is happening in the pore scale with an appropriate grid resolution refinement that we need in that region. And whereas in the other part of the system, we can keep it at a very coarser scale, which will be a very important factor in the future generations of simulators, so that we can capture everything accurately.
Perfect. If there is no more question, I think now we can wrap up this session. Thank you once again, Ankita and Mousa, for your time and these great talks. We wish you good luck with your future work.
Thank you.
Now to our next session. if we have the, yeah. Our next session, the last Porous Media Tea Time Talks of the year, in 2 weeks, will be given by Mehdad Ahkami from ETH Zurich on experimental study of fluid flow and solute transport in fractured porous media. And the second presentation will be delivered by Tapomin Bhattacharjee from Princeton University on bacterial motility in porous media. I want to thank you, our audience again. Thank you for your support, comments, and suggestions. Please help us improve this platform for PhDs and young researchers by contacting us at porousmediattt@gmail.com. With this, we will say bye, and we hope to see you in 2 weeks for the last session of 2020. Have a nice day. Bye-bye.